Swayam Prabha. Digital India. Educated India.
Today we are going to talk about beam on elastic foundation. This deals with certain analysis which has number of applications. Let us consider some of these applications. Many times you will find that pipelines are made up of segments which can be of different geometry or they can be made up of different materials. Look at this particular application. Herein we have pipe of uniform cross section. The portion on the left is made up of a material whose modulus, coefficient of thermal expansion, Poisson's ratio is different from that of the pipe which is on the right hand side. You find that in power plant applications, when the temperature is high, then the vessels are made up of stainless steel and the portion of the components which are away from high temperature region, they are made up of ferritic steels. So, one can have this portion made up of stainless steel, this can be made up of ferritic steels, and these materials they have different coefficient of thermal expansion, though their modulus and Poisson's ratio may not differ significantly. Similarly, you can have pipelines wherein the radius of the pipeline is different from one segment to another segment, although the pressure is same, and also you find that the thickness of the material is different in the different segments. This will give rise to some problems. Let us look into that. First of all, if you think of this case, this pipe, if the temperature of the pipe is raised by delta T, and think of a situation that you have this coefficient of thermal expansion alpha 1 is greater than alpha 2. So, what you expect is that this pipe on the left is going to expand radially by some amount, let us say u1, and the one on the right is going to expand by some amount, let us say u2. Obviously, this expansion u1 is more than u2, and hence at this junction you find that there is mismatch in the expansion, and this will give rise to some stresses in the neighboring region. So, these are local stresses. Look at this case, herein you have the thickness is large, and therefore, you expect this pipe to expand radially by some amount, let us say again it is u1, and the one on the right is thinner, it is subjected to the same pressure. So, it is going to expand more, and this is going to be u2. So, you find that because of the internal pressure there is going to be some mismatch in the radial expansion, and this will give rise to some stresses in this neighboring region. Another problem which is also very common, you find many cases cylindrical vessels have closures which can be flat, which can be ellipsoidal, which can be spherical. So, let us just look into the case that you have the cylindrical vessel and the head is spherical, they are made up of the same material and they are subjected to the same internal pressure. Now, you know that under the action of the internal pressure in the cylinder, you are going to get both hoop stress and also the axial stress. Similarly, in the case of spherical vessel, you are going to get both hoop stress and axial stress. And if you now consider the thickness to be the same, then this cylindrical portion is going to have expansion under the action of the internal pressure. Let us say that is going to be UC is the radial expansion, and similarly the head portion or the spherical portion, that is going to expand also radially, and this radial expansion is going to be, let us say, like this, and this amount is equal to UH. It can be very easily obtained, since the circumferential strain is given by U by R. U by R is nothing but sigma theta by E minus nu times sigma A by E, and the hoof stress is PR by T and the axial stress is PR by 2T. Therefore, from that you can get this UC for the cylindrical portion is nothing but PR square by 2T E into 2 minus nu. So, that is the radial expansion of the cylindrical part. And if you consider the spherical head, that spherical head is going to have expansion in the radial direction, which is nothing but PR square by 2T. In this case, both the stresses are of magnitude PR by 2T, and therefore, you will get the expansion is nothing but this much. Now, if you look into nu is generally very small, if we forget about that part, the expansion of the cylindrical portion is going to be almost double. So, therefore, you get the expansion of the cylindrical portion is very large compared to the head expansion, and therefore, you find that this portion is going to have mismatch under the internal loading, and that will give rise to some local stresses. So, on top of the stresses that you calculate by considering the hoof stress, axial stress, you are going to get some local stresses coming up here, and those local stresses are to be estimated. So, in all these applications you have similarity, that you have some mismatch in the expansion of the vessel in the two segments, and then you are interested in trying to estimate what is the order of magnitude of the local stresses. And in fact, it is possible to estimate the magnitude of these local stresses by using the concept or the analysis which is associated with beam on elastic foundation. So, that shows the importance of the topic. So, let us consider how we go about talking or analyze the stresses in the case of beam on elastic foundation. Let us consider one beam which is like this, and the foundation is shown here. Now, this is just a beam of some dimensions, it will have some height and then width, and it is resting on the foundation, and we subject it to some external loading P. It is not, the difference is that this foundation or the support is not rigid, and if this is not rigid, then in that case what you find is that you are going to get this beam deflecting, and it is going to deflect more under the load, and it is gradually going to decrease as we move away from the load. And therefore, what you find that the reaction that this support is going to give rise to is not going to be uniform. So, the reaction that is going to come up at the contact surface is not going to be uniform. Let us consider that that reaction of the support is going to vary, it is going to be varying like this. Let us say arbitrarily we consider that there is a variation, and that variation we assume that it is proportional to the deflection that comes up in the local region. So, if you are considering the reaction here, it is of magnitude k into y, where y is the deflection there. So, we just make use of our symbol like this. This is x axis, this is y axis, y is positive downward. Now, let us try to see that this is nothing but you have this case beam, like you have a beam which is now externally loaded like this, and it is supported, or it is going to have support reactions varying like this. So, let us try to see how we can get the deformation of this beam and how we can calculate the stresses in this beam. Let us concentrate on a portion somewhere here. So, let us just take a segment which is of length equal to dx. So, we will just concentrate on a segment which is of length equal to dx, and if we draw it to a larger scale, I have shown it here that this portion is now subjected to load intensity Q, and the shear force is V on the left and bending moment is M there, and therefore, we are going to have shear force on the right hand face is V plus dV and the bending moment is M plus dm. So, if I now consider the equilibrium in the vertical direction, then you find that this you have dV V plus dV and this is acting upward. So, therefore, differential is dV and that dV is nothing but q into dx, and therefore, we have dV dx is equal to q. So, from the equilibrium consideration in the vertical direction, what we get is that dV dx is equal to q. This is a relationship which you have also derived in your first course. The sign could be different, that is all. So, let us consider this is equation number 1. Similarly, if we consider the moment equilibrium, then if we consider the moment here, let us say that anti-clockwise moment is positive, then this will be acting clockwise. So, the differential moment is dm. So, that dm is now balanced by, if I consider moment about this point, it is v into dx and then q into dx by 2, they are acting in the same direction. So, therefore, we can write now that dm and then it is v plus dv into dx. So, it is in the opposite direction, and then we also have, I am sorry, this should be negative. So, therefore, this is minus q dx square by 2. So, that is the equilibrium equation in terms of moment. And now, herein what we have is that we have v into dx, dv into dx and dx square by 2. When you are trying to think of this dx shrinking to 0, then in that case we will have no contribution, this we can forget, and therefore, this is also product of two small quantities we can forget. Therefore, what we will have is dm equal to v into dx and therefore, dm dx equal to v. So, that is another relationship or feature that you have already seen in your first course. Now, we will consider the moment curvature relationship. Moment curvature relationship, in this case the beam is going to have bending like this, and therefore, center of curvature will be upward, which is located in the negative y direction, and therefore, the d2y dx square should be equal to minus 1 by r, where r is the radius of curvature, and therefore, now we can write d2y dx square is equal to minus m by ei. So, that is the moment curvature relationship. So, now, having got it, now we can do little bit of manipulation on it. If I now try to write d3 y dx cube, nothing but it is dm dx. So, therefore, that will become v by ei. So, I simply substitute dm dx is equal to v. Similarly, if I differentiate it once more, dx4 d4y dx4 is equal to minus q by ei. So, that is the equation which is the deflection equation of the beam on elastic foundation. Now, since q is equal to ky, we can now write now d4 y dx4 plus k by ei into y is equal to 0. So, that is the equation. We can write this thing 4, that is the equation governing the deflection. Now, this is a standard equation. Its solution can be written in this form: y is equal to e to the power beta x into C1 cosine beta x plus C2 sin beta x plus e to the power minus beta x into cosine beta x plus, I am sorry, there should be C3 here. So, we should have C3 cosine beta x and C4 sin beta x. That is the solution. That is the solution, wherein this beta is nothing but fourth root of the ratio k by 4 ei. So, that is the beta factor, and since it is a fourth degree equation, you expect 4 arbitrary constants C1 to C4 are involved there, and this ei is modulus of rigidity. Modulus of rigidity of the beam section. We have to now see how these constants can be resolved, and that is possible by taking specific example. So, let us consider one example wherein we have a beam. We will just try to think of this case itself, that we have a beam on elastic foundation and it is subjected to concentrated load and the cross sectional rigidity is ei. Now, think of the physics of the problem. If you think of the physics of this problem, the deflection as you go away from the origin, whether you move to the right or the left, you expect sorry, the deflection to gradually die out. So, therefore, with increasing x, your deflection must die out, and if you see the solution that we had obtained here, it shows y equal to e to the power beta x C1 cosine beta x C2 sin beta x plus e to the power minus beta x into C3 cos beta x plus C4 sin beta x. Obviously, if x increases, if beta is a positive constant, and therefore, this term is going to shoot to infinity, and therefore, we cannot have these things present. For a problem of that type, our solution should be certainly y equal to e to the power minus beta x into C3 cosine beta x plus C4 sin beta x. So, that is the specific case that we have, and therefore, at x is equal to infinity, what we ought to have is that C1, C2 must be equal to 0. So, they must vanish. So, for this problem, the logic is for finite displacement or deflection, at x is equal to infinity, C1, C2 must be 0, and therefore, our solution for the specific case is y equal to e to the power minus beta x into C3 cosine beta x plus C4 sin beta x. Think of it, how do you resolve these constants? We have to make use of the loading conditions and also the boundary conditions. What are the boundary conditions that we can a priori specify? Obviously, one condition is that this beam is going to deflect symmetrically, and therefore, we expect the slope at origin should be 0, and at the same time, the reaction that is coming up at the bottom of the beam is going to be k into y at different locations, and therefore, if we now consider the sum up of the forces from x equal to 0 to x equal to infinity, we must have the load double of that. Obviously, it is a symmetric problem, therefore, double of that must be equal to the external loading. So, I repeat this point, that you are going to get reaction to be k into y, and if you now see that that same position is going to be exactly on the other side at the same distance. So, therefore, if we sum up the reaction from x equal to 0 to infinity and double of that, that should be equal to the external loading. So, these are the two things that we can make use of. So, therefore, we must have dy dx is equal to 0 at x is equal to 0, that is the symmetric shape, and this derivative we can write therefore e to the power minus beta x into minus beta c3 cosine beta x plus c4 sin beta x plus we differentiate now the expression inside. So, we will have beta coming out. So, we can take that minus c3 sin beta x into beta, that beta I have taken out, c4 cosine beta x. So, that is the full derivative, and therefore, at x is equal to 0, this is 0. So, that is equation number 5, and this gives us x equal to 0, this is unity, and therefore, we are going to get minus c3 into beta, and here again we are going to get c4 into beta. So, beta can be removed, and therefore, we have c3 plus c4 is equal to 0, that is the expression, and therefore, c3 equal to c4, and let us say that that is equal to a constant without suffix, and that is equal to c, let us say. So, now we have got y is equal to c e to the power minus beta x into cosine beta x plus sin beta x, that is the value of deflection. Now, if we try to consider the reaction at every point and then try to sum up, that will give us this expression. So, P equal to twice 0 to infinity k times y e to the power minus beta x cosine beta x plus sin beta x dx. So, this is a case of product of two functions e to the power minus beta x and cosine beta x plus sin beta x. So, we can do it integration by parts. So, therefore, if we do that, twice kc, first we integrate this, we take this as the first function. So, therefore, we will have e to the power minus beta x by minus beta cosine beta x plus sin beta x. This expression, it is to be evaluated at infinity and 0 minus 0 to infinity integration of this first function, differentiation of the second function. So, sin beta x plus cosine beta x into beta into dx. So, that is the expression. And now if you try to evaluate this thing at infinity, e to the power minus infinity will become 0. So, therefore, this gets knocked up, and then if you try to evaluate at 0, this is unity and it is going to be minus this quantity at x equal to 0. So, this will become unity and this is 1 by beta, and this is going to be 1, this is 0. So, therefore, it is minus 1 by beta, and that minus minus will give us plus 1 by beta. So, this finally becomes 1 by beta 0 to infinity minus e to the power beta x cosine beta x minus sin beta x into dx. Now, we continue further. So, if we continue further, this will give us twice kc 1 by beta plus, again we do the same procedure here. So, e to the power minus beta x by beta minus beta cosine beta x minus sin beta x 0 to infinity minus 0 to infinity minus e to the power beta x minus beta minus sin beta x minus cosine beta x into beta into dx. So, that is the expression. Now, look at this. This one comes out to be, this minus will be absorbed. So, they will cancel, and therefore, we are going to have 0 to infinity e to the power minus beta x by beta, and this beta is going to cancel with this beta into sin beta x plus cos beta x. And if you look into the initial expression, so we have here, see this expression, it is similar, e to the power minus beta x into cosine beta plus sin beta. So, therefore, this is 0 to infinity. So, therefore, we can write this thing, this expression as p by 2 kc. So, this is nothing but repetition of that, and therefore, we can write now twice kc, and this is going to give us, again by similar consideration, it is going to be 1 by beta only. So, therefore, we will have 1 by beta plus 1 by beta, and so let me just write that this is nothing but e to the power beta x into cosine beta x plus sin beta x dx. So, that is the simplification, and therefore, now we substitute for this p by 2 kc, p by 2 kc, and therefore, we get the following. So, therefore, you get that it is 2 kc p by 2 kc, and therefore, this is negative, it will go to the other side, and therefore, what we find finally that, okay, let me write this one, that this is nothing but p by 2 kc. So, this 2 kc will cancel, this p can be taken to the left hand side, and therefore, we have 2p equal to 2 kc into 2 by beta, and hence this constant is equal to p beta by 2k. So, that is the constant of integration for this particular problem, and hence we have finally the solution y equal to p beta by 2k e to the power minus beta x cosine beta x plus sin beta x. So, that is the expression for y. Now, this is represented many a times, this is a standard function, there are tables available for this function. So, it is many times represented as p beta by 2k into a beta x. So, this a beta x function is nothing but this one. So, that is what is a beta x. Once you have got that deflection, it is possible to calculate the you can calculate the slope, bending moment and shear force at every cross section. Obviously, when you are interested in calculating the stresses due to bending moment, you must have the value for bending moment. So, it is worthwhile trying to see how the expression for bending moment, shear force at a particular section can be obtained. So, we will do that. We write that theta slope is nothing but dy dx. So, this dy dx simply we have to differentiate once. So, if we differentiate this e to the power minus beta x minus beta for the first function and then cosine beta x plus sine beta x plus e to the power minus beta x into differentiation of this will give us sine beta x plus cosine beta x into beta. So, that is what is theta, and this we can see that there is some cancellation, that this beta cosine cos beta x into beta is cancelling with this term. So, these two terms gets cancelled and therefore, we have p beta square by 2k into minus 2 e to the power beta x sine beta x. So, this is represented as b beta square by k e to the power minus beta x sine beta x. Again, this is again a standard function, and in fact, we represent this thing as b beta x, and therefore, with this symbol we have theta is equal to p beta square by k into b beta x. So, that is again the value of this function is available in tables. Now, bending moment, we can write this bending moment as m ei d2y dx square, and therefore, it means that you have to differentiate, and this we can write for ei as k by 4 beta raised to the power 4, since k and beta ei related. So, we substitute that into minus p beta square by k differentiation of this expression here. So, therefore, it is we take directly this one, and therefore, it is e to the power minus beta x into sine beta x this, and this finally gives us which is quite simple. So, I will skip this step and let us write this is equal to p by 4 beta e to the power minus beta x cosine beta x minus sine beta x, and herein again we write this function as c beta x, and therefore, with that symbol it becomes p by 4 beta into c beta x. So, that is the value for the moment in terms of the sine beta x, cos beta x and e to the power minus beta x. Let us try to see what is going to be the value for shear force? Shear force is equal to minus EI d3y dxs cube, and we can again try to take the value for d2y dx square, which we have already got. So, once we try to take the value of d2y dx square from this relationship, so finally this gives us, it is nothing but p by 4 beta d dx e to the power minus beta x cosine beta x minus sin beta x. So, we have this expression, and this is again routine function which you can easily differentiate, and finally what you get out of it is nothing but p by 4 e to the power minus beta x minus twice cos beta x is equal to p by 2 e to the power minus beta x cosine beta x, and this we represent by d beta x, and therefore this expression becomes minus p by 2 d beta x. So, we have got all the quantity of interest, deflection, slope, bending moment and shear force. So, the expressions finally that we have obtained are written together. A beta x is equal to e to the power minus beta x into cosine beta x plus sin beta x. B beta x is e to the power minus beta x into sin beta x. C beta x is e to the power minus beta x into cosine beta x minus sin beta x. D beta x is e to the power minus beta x into cosine beta x. Mathematical tables are available wherein the values of all these functions are given in terms of beta x. Now, these functions will give us some idea, if we look into them, about the variation of the deflection, slope, bending moment and shear force. So, you see that these functions are oscillatory and they have amplitude of the function gradually reduces. So, therefore, if you consider the function y is directly related to a beta x, so the plot of y, so also a beta x is like this. You expect that there will be large deflection at this point of application of the load, it reduces and then it really tries to lift up the support and then again it goes on decreasing, the deflection is actually going to be positive. So, here it is positive, negative, positive, and the period of the function is 2 pi by beta and this is pi by beta. So, therefore, you find 0 to be somewhere about 3 pi by 4 beta, and this is 0, and here it is 7 pi by 4 beta, another 0. So, the nodes are here and here, it is 3 pi by 4 beta and this one is 7 pi by 4 beta. The variation of the slope, this is a symmetric function, a beta x or deflection is a symmetric function as we expected, and this b beta x is anti-symmetric function and its shape is going to be like this, and it has a node at pi by 4, another node at 2 pi by, I beg your pardon, this is pi by beta and another node at 2 pi by beta, and this amplitude is gradually reducing as you move away from the origin. So, that is the variation of slope. And variation of bending moment is like this. Here it is a symmetric function, and this symmetric function is going to have value like this, and it is having some amplitude there, and again it changes. Likewise, the variation of the shear force is antisymmetric, and this is how it varies. So, you find that one function is symmetric, the next derivative is antisymmetric, and it goes on. So, that oscillation takes place. Now, we will try to go for consideration of a beam which is semi-infinite. It is not infinite, it is semi-infinite, and try to see how we can find out the deflection, bending moment variation, so also variation of shear force and the slope. So, the beam is like this with rigidity EI, and it is subjected to now loading, concentrated loading P0 at origin, and also bending moment, which is positive bending moment. This shear force is it is a negative shear force, because we consider on this face it is negative phase, shear force is acting upward is positive. So, this is a negative shear force. Looking at the fact that the deflection should gradually diminish as we go towards infinity, and we can write the governing equation is going to remain the same, and therefore, we can write the solution for this problem also in a similar fashion as we have done in the other case. For the semi-infinite beam, we can write the deflection in the form. So, let us write the deflection equation in the form y e to the power minus beta x into C3 cosine beta x plus C4 sin beta x. If I now try to write dy dx, so we have product of two functions, it is not difficult to write the derivative. So, it will be e to the power minus beta x minus beta into C3 cosine beta x plus C4 sin beta x, plus we can now keep the first function same, we will differentiate now C3 sin beta x into beta C4 cosine beta x into beta, we can keep it outside. Similarly, if we now write d2y dx square, this is going to give us e to the power minus beta x, and this minus beta will give us beta square into C3 cosine beta x plus C4 sin beta x plus e to the power beta x. If we take the beta which is going to come from differentiation of this, we can take it together. So, therefore, this will be minus beta square into C3 sin beta x, beta already we have taken out, plus C4 cosine beta x. So, that is from the first expression. Similarly, we will have from the second one e to the power minus beta x, this will give us minus beta, that minus beta will get combined. So, it will be beta square into C3 sin beta x plus C4 cosine beta x plus e to the power minus beta x, and the differentiation of this will give us another beta which can be combined together. It will give us beta square minus C3 cosine beta x minus C4 sin beta x. Sorry. If we now consider that x equal to 0, the derivative at x equal to 0, then we have these terms will become unity, and then only cosine terms will give us contribution sorry, C3 beta square, and here it is C4 minus C4 beta square, and here also we are going to get C4 beta square. So, therefore, it is twice C4 beta square, and here it is minus C3 beta square. So, C3 cancels out, and therefore, we can now have only minus 2C4 beta square, and we have the value m0 is equal to minus ei d2y dx square at x equal to 0, and therefore, now we can write that is equal to minus ei into minus twice C4 beta square. So, we will get C4 in terms of m0. Similarly, if we calculate d3y dx cube at x equal to 0, this will give us 2 times beta cube into C3 plus C4, and since we have v at x equal to 0 is equal to minus P0, and that is equal to minus ei d3y dx cube, then we can relate these, and this will give us finally an equation involving C3 and C4, and we can solve for C3 now since C4 is known. So, finally, what we have is that C3 is equal to P0 minus M0 beta twice ei beta cube, and C4 is equal to M0 twice ei beta square. And we can now write the deflection is nothing but y equal to e to the power minus beta x into m0 twice ei beta square sin beta x plus P0 minus m0 beta twice Ci beta cube. So, we have substituted value of C3 and C4 this into cosine beta x. So, that is the expression for the deflection, and we can recombine these and write the value in terms of k, because beta 4 is nothing but k by 4 ei. So, if we make use of this, then we can write this y as twice P0 beta by k e to the power minus beta x cosine beta x plus twice m0 beta square by k e to the power minus beta x into sin beta x minus cosine beta x. So, that is the value for y, and this can be written in terms of the standard functions that we have introduced, twice p0 beta by k d beta into d beta x minus twice m0 beta square by k into c beta x. We can get the expression for theta. Theta is equal to dy dx, that is equal to twice p0 beta square by k. If we differentiate this, it will give us minus 2 beta b beta x. So, therefore, this can be written as the minus 2 p0 beta square by k, that is a beta x. Once you differentiate it, it gives you twice beta into b beta x. That is what I have adopted here, and this also will give us, differentiation of this will give us, c beta x differentiation will give us minus twice beta d beta x, and therefore, this finally gives us twice m0 beta cube by 4 times m0 beta cube into d beta x. Similarly, we can write now m. So, I can take now double derivative and then write finally expression for m. M is going to be p0 by beta, this a beta on differentiation will become b beta x plus m0 d on differentiation will become a beta x. Similarly, the shear force is nothing but p0 c beta x minus twice m0 beta into b beta x. So, these are the expressions for deflection, slope, bending moment and shear force, and we if we evaluate the value of deflection at x equal to 0 and slope at x equal to 0, then if we represent the deflection at x equal to 0 as y0 and slope as theta 0, then from the expressions that we have derived we get y0 is equal to, it will be 2 times p0 beta by k minus 2 times m0 beta by k, and theta 0 is equal to minus twice p0 beta square by k plus 4 times m0 beta cube by k. These are the deflections and slope at the origin. We will see how these results can be made use of in estimating the forces that develop at the discontinuity of pipes or maybe junction of cylinder and the head of the cylinder.